Okay, so this is part two about scatter plots. And this is more so about using our technology to calculate those lines of best fit that we were talking about in our previous video. And so this is called linear regression. Now, once we learn our other families of functions, our exponential, our quadratic, okay, we can have other types of regression. We're like, okay, what's going on with our data? It looks like it's in a line, or it looks like it's in this type of curve. That's how you're going to be able to tell what type of regression you're going to do. But in this case, we only know lines so far. So we are doing a linear regression. So we're saying we have some data. We believe the data is kind of modeling in a linear fashion. So we are going to tell our calculator or whatever other technology we are using to figure out what a good line would be to model that data. Okay. So the first part here is using a graphing calculator. Uh, that's actually a lot of steps. So, and it's kind of complicated. So I'm not going to show you that right now. But we are going to at least look at a picture of a graphing calculator and what you would see and know what the letters and things are telling us. And then I will also kind of give you a rundown on Desmos of what to do. And we'll use that to do a question towards the end of the video. Okay. So once again, this picture up here is of a graphing calculator screen. Someone has put a bunch of data into this calculator, run the regression, and this is what pops up. So notice, first of all, that it says y equals ax plus b. For some reason, the calculator does not use our normal letters. So it's just like y equals mx plus b, but they're using a for m instead. But they mean the same thing. Okay. So in this case, a is going to be the slope of our line, and b is the y-intercept. So if we're looking at this information on the screen, obviously they give us lots of place values, so let's just round it to the nearest tenth, we'll say, okay? It would be y equals our m or a is going to be 13.6 if I round according to that. So 13.6x. And then my y-intercept is the b, which would be approximately 17.6. And that would be our line of best fit based on what was entered into this calculator for whatever data was being used in this question. Okay. On Desmos, I will show you how to do this later, but just here's our rundown. There's going to be a place with a plus sign, and you can say, let's add something in here, and we can create a table. And then there is going to be a wrench that will allow you to adjust your axes to kind of see your data a little bit better. And then when you want to do a linear regression, you would type this in into the next line of your Desmos, and then it will tell you what your slope and what your intercept would be based on your data. Okay, so we'll do that a little bit later. So now there's some other things on this calculator screen. Okay. One of them is the correlation coefficient. The correlation coefficient is going to be that R. Okay, this one right here. The correlation coefficient tells you how closely your data models a line in this case, or models whatever type of thing you were asking it to model. Okay. Correlation coefficients run between -1 and +1. And the reason it is -1 and +1 is because we have negative correlations and positive correlations. Okay. Remember, negative correlations start high, go down. Okay. Positive correlations start low, go up, just like slopes. So if it's really strong, well, actually, I should say, if it's perfect, like all of the points in your data exactly mirror the line that you're using, it's going to be either -1 or +1. Those are perfect correlations. Okay. If you have something close to -1 and +1, because that's not usually going to happen when you're collecting data for something, it's never going to be perfect. Okay, but if you have something that's really close to -1 or really close to +1, those are going to be really strong correlations. Okay. The data is pretty close to a line, and a line is a really good tool to help you model it. Okay. If it's kind of scattered more all over the place, you'll see it start getting closer to 0. Where 0 would once again be like no correlation going on here. Like it's almost saying, why the heck are you trying to use a line to model this? It doesn't really make sense. Okay. So it ranges between that -1, which is a strong negative correlation, to a positive one, which is a strong positive. So if we're looking at these examples down here, okay, our first one has a positive correlation. Okay, we see that line of best fit that was drawn within the data, and that is really, really close to that line. So you can see that the correlation coefficient is 0.984. It's pretty close to 1. So if we were analyzing this, we could say this has a very strong positive correlation. The next one, like, kinda maybe we could use a line here. I'm thinking if I just looked at the data, I would probably say there isn't really a whole lot of correlation going on at all. But they did create this line of best fit. You can see that our points are really, really far for that line of best fit. However, they're saying there is a negative correlation, but it's not very good. So you can see that that correlation coefficient, that R, is close to 0. So this would have a weak negative correlation. And then finally, the last one, our data points, our line of best fit. All those points are really close to that line of best fit, but it is a negative correlation in this case. So this would be a very strong negative correlation. I'm going to abbreviate it. Okay. And then maybe if it's like 0.7 something, you're like, there's a fairly strong positive. Okay, you can use other describing words there as well. But definitely the closer it is to 1 or -1, that's very strong. The closer it gets to 0, that's going to be pretty weak. Okay. Our last page here, this is going to be on making predictions. So a lot of you are saying, why do we need to know this? And a lot of times, let's be honest, there's things we do that you probably will not really need. But if you're going to be going into something where you're going to be in a job that's analyzing numbers, okay, you are going to be doing modeling. And yes, the technology is going to be the ones that probably do the modeling for you, but you have to be able to analyze what the technology gives to you. So this is where this comes into play. So we have a picture that shows regional air travel data recorded by a domestic airline company. How can you use the data to estimate the number of air miles people flew in 2003? If the trend continues, what is a reasonable estimate for the number of miles that people will fly in 2030? So, first of all, we talked about this the other day. When we are building an equation and what we are plugging in is time, we usually don't plug in like the years or the actual time. We said we pick a starting point and then we go like number of years or number of days since that starting point. So here in our graphic, the first year is 1975. So we're going to say, let's let X equal the number of years since 1975. That's going to be our starting point. Which means when we go to make our equation, once again, our X isn't going to be the number of years. So for the first one, 1975, that would be actually like an X of 0 because no years have passed since 1975. 1980 means that would be like an X of 5 and then 10 and so forth as it keeps going. So we're saying X is the number of years since 1975, and then we can adjust our X values from there. So we are going to use our Desmos to create our line of best fit. So I'm going to hop over to Desmos. Okay, now I do have it preloaded on my other screen, but I did want to show you what I mean by the plus sign. So on the left-hand side of our screen, there is a plus. And then when you click that, there is a spot for table. And then you would enter your X values and your Y values. Okay, and then the next line down is where you would enter that equation I told you to type in that gives you that linear regression. So I'm going to pull it up on this screen here. Okay, you can see I have my chart, okay, loaded. But if you look at my graph, you don't see anything. And the reason is my graph is currently going from an X of -10 to +10 and like -8 to +8, which based on my data, like you're not going to see anything there. So this is where changing your window is going to be helpful. And to do that, there is a wrench in this top right corner, which is graph settings. Okay, and I'm going to change the scale on my X and Y axis. So my X axis, I'm gonna have to flip my computer around. Yeah, a sec. I'm gonna flip my computer around because I'm going to change my X axis. We'll say -5. I usually like to go a little bit lower. I know it starts at 0, but we'll say -5. My biggest X, if I keep extending that, I believe was 40. So we'll say, like, let's make it go to 50. Okay. And then from there, my Y axis is, I'm going to make it start at 0. I know the first one's really at 1298, but we'll say let's start at 0. And the biggest Y value is 3055. So I'm going to say let's go to 3500. And now you can see the data points from the table because I have adjusted my min and max X and Y's to fit what's going on here. Okay, now sorry. Okay. And now on the left-hand side, on my other part, you can see I have typed in that linear regression. Okay. When you do Y1, if you just hit 1, it automatically makes it that subscript. You don't have to do anything fancy there. And that little squiggly is like in the top left side of your keyboard. Okay. And I'm going to now turn this on so you can see the line of best fit. And Desmos is telling us that based on our linear regression, that would be our line. Okay. And they do M and B. So it gives us our M is 37.87 and our B is 1322. And actually, I feel like I made a mistake somewhere. So let me just check my data because that's not the numbers I had before. That one right there. I had 2 wrong data points. So that would be why. So let's change this one. This one's supposed to be 2697. This one's supposed to be 2973. There we go. That looks a little bit better. Sorry about that. So now it has automatically adjusted our new line of best fit, and that looks more like what I had before. So that is good. So our slope is 47.87 and our y-intercept is 1345.04. I'm now going to go back to our notes and I'm going to say that Desmos told us that our equation should be y equals 47.87x plus 1345.04. Okay, so that's our line of best fit, but now it's asking us to do some estimating here. Now, 2003 was within the range of our data, but it wasn't one of the dates listed. It jumped from 2000 to 2005. So they're saying, based on this, now that we have our line of best fit, what would be a reasonable estimate there? So if it's 2003, if we're saying number of years since 1975, that would mean that our X would actually be 28. So what we would do is we would just now take that X and plug it in to that equation we just got. And I would certainly be using a calculator to do this. And when you type that in, you would get 2685.4. But now keep in mind, it says in thousands. So let's throw 1,000 in there to be accurate. Okay, so that would be our estimate for 2003. Okay. Now 2030 extends beyond that. Okay, but we can still use our equation to make a prediction here. But that would mean that that is 55 years from 1975. So we're going to plug in 55 into our equation. So 47.87 times 55 plus 1345.04. Once again, crunching numbers on a calculator, it would be 3977.89 thousand. Okay. Now there are some fancy vocab words that go with what we just did. And that would be interpolation and extrapolation. They sound fancy, but they just mean, ooh, roll down on me. These are fancy words that mean to estimate or predict. The only difference is like the date range of what's going on here. So interpolation is using a model to estimate a value within the range of known values. Okay. So we were looking at 1975 to 2015. When they were asking us to look at 2003, that was between the data we already have. So that guess was interpolation. Okay. When they were asking us to look at 2030, that was beyond the scope of 2015. So that was called extrapolation. Okay. It was beyond the last data point. They both mean estimate, they both mean predict. Okay. And it's just talking about, is it within the data or outside the range of data? I will note that this one is less accurate because once you go beyond the scope of data, things can change. Just think about it. 2020, which would have been the next data point. Okay. We all know global pandemic hit and people weren't really flying anywhere. Okay. So if you added 2020 into this data, okay, its numbers would probably be far below where you would have expected them to be based on the trend that's going on. Okay. The last thing, this is very easy, not super important, but the last thing is about causation. So causation describes a cause and effect relationship, meaning a change in one variable causes a change in the other variable. The number one thing I want you to get out of this is correlation does not imply causation. Just because you're saying there's a relationship between things going on, whatever data you're looking at, okay, you can't directly say that one thing is affecting your other. You would have to like set up an experiment, have a controlled group, okay, test your things accurately. Okay, so you cannot just say that because there's correlation, that one thing definitely caused the other. Okay, I think when you do a math Excel, you will probably see this phrase correlation does not imply causation. Okay, and that is our work with scatter plots. And hopefully your practice isn't too bad. Let me know if you have questions.